Finally, we can start. Good afternoon, everybody. Actually, we are just 12 minutes late because everything was shifted. So it doesn't sound as bad as 42 minutes late. We have for now Jeff Denworth, co-founder of VASTDataduring, and Jeff Rivolto from Quanta Technologies. And please, you can start your presentation.
Okay, and time-wise, how long are you 15 minutes?
You should have 20 minutes, but I asked you to shrink it perhaps to 15, so we can have time for some Q&A.
No problem. Okay, so let's start a little bit with who is VAST, and then we'll talk a little bit about what VAST makes. We started the company in 2016 with an idea on how to make not only storage much simpler from the perspective of unstructured data and structured data, but also with an idea that we could potentially reimagine data processing. And so the company started selling in the early parts of 2019, and we came out to market with this idea that you could build a single tier of enterprise flash that was affordable enough for all of your data. It was simple enough that you could deploy it across the enterprise, and it was performant enough that you wouldn't need solutions like parallel file systems anymore. Now, that implied in that is that the system supports standard storage interfaces like NFS and SMB and S3. And that was a pretty radical message, in particular to HPC practitioners, and then increasingly to AI practitioners that were getting a formula or a recipe from NVIDIA. And having said that, we had a few very progressive customers that chose to take the journey with us and prove the thesis that we laid down in 2019. That became the kind of the foundation that we started to build on. Today, we've probably shipped about 20 exabytes of infrastructure into the market. We are proud to call many of the world's largest AI computing centers and AI or HPC centers, some of the largest as our customers, and we're really just getting started. The company was valued at $9 billion late last year, which makes us the most valuable private storage company in history. And what I'm going to talk about today is largely things that we've done to work beyond the classical definitions of storage. So to start, we had to kind of reinvent storage. And how do we do that? Well, let's start here. So the last 20 years of scalable systems largely based on a systems architecture that wasn't born out of Google, but was definitely popularized by Google, an architecture called shared nothing, where you can build large clusters of systems that you break a namespace across a number of standard commodity nodes, and you kind of build out systems as such. Now, the problem with that approach is that anything that's transactional that happens into the system, all of the nodes need to stay in constant communication with each other. And so the Google architecture ultimately became the basis for services like Hadoop or Isilon in the file system space, which is a very popular file system. Most major object storage systems, hyperconverged systems, are all built on this idea that you can break namespaces across commodity shared nothing nodes. The challenge becomes that you can't transact into these systems at all. So they're great for reading, great for capacity, not good for transactional performance. And most importantly, what we saw is none of them are good for flash. And so in 2016, we started talking with a number of industry partners as we started the company. And what we realized is that fast networks, in particular, NVMe over fabrics, which is a set of verbs that run either on Ethernet or InfiniBand networks, could make it possible to decouple CPUs from SSDs. If it takes 5 microseconds to get from a CPU to an SSD on a motherboard, it only takes 10 microseconds to get from a CPU to an SSD that could be on the other side of a data center. And so now you can build systems that have the capabilities and the performance profiles of direct attached systems, whereas you can completely break apart clusters and have just a host of stateless cores that all access a bunch of SSDs. Now, all access is the most important and most difficult part of our story, in that we had to build a new data structure. A data structure that would make it possible to take all of the SSDs that you have in your data center and organize them into a single volume that all the cores can see and transact into in parallel. And so the consequence of this is we built the world's first partitionless system that you could scale to an exabyte. We basically put the problem on the network, the NVMe fabric, with the understanding that when Google introduced their architecture 20 years ago, networks were very slow. Today they're 800 times faster than they were when we decided to move to this shared nothing direct attached world, making it possible to disaggregate. And so what comes of this is a system where you just have parallel paths that talk to your data. And think of these machines as containers that are one part file server, one part database server, one part application runtime environment that runs in a standard Linux image, and you can have hundreds or thousands or tens of thousands of these in your data center. So it is, in essence, a distributed computer. You think about these machines as cattle. You can lose whole hosts of them. You can lose all but one machine in your cluster, and you're still online. Everything is always online from a management perspective. All upgrades are online, all expansions are online, and basically all of the data services that you need can be serviced from this single platform. Now, Flash is really, and particularly when we started, Flash is very expensive. So we invested a ton of our time making it such that you could afford Flash for all of your data. We did this with a new approach to global compression that we call similarity. If you've worked with vector databases at all, you'll know the same, or search engines, the same search mechanisms that run in those systems that work on a statistical basis are the search methods that we use within our system to find blocks that are close to each other so that we can compress them together. This, in the high-performance computing and AI space, nets our customers somewhere between a 2 to 3 to 1 data reduction advantage. And the consequence of this is that then that's the only storage system that you need in your environment, because now you've got something that has the performance properties of your high-performance systems and the cost properties of your archive. So, so we call this DAYS. It stands for disaggregated and shared everything. And this is the thing that allows us to basically do whatever we want to do. All the cores in the system can transact into a shared namespace in parallel without talking to each other. There is no east-west traffic in the system. So as we stood up database services, we said, why don't we do things like add a transactional database that's ACID transactional? Why don't we support things like Kafka services natively on top of a data warehouse, such that you don't need an event bus and a data warehouse anymore? These all converge into one. And that, in particular, has been a really successful strategy. I'll talk with you about how we talked to it in a second. Now, earlier this year at GTC, we took some time to show the world about a new application of this system. And if you followed what NVIDIA's been doing for the last 2 years or so, they've been more and more putting intelligence at the network endpoint within clusters using a technology called DPUs, which stands for Data Processing Unit. A DPU is basically an ARM processor that's glued onto a network adapter. And for some time, these were solutions without a problem. CoreWeave, which is one of the world's largest GPU hosting companies, basically said, I could use these as VAST servers. And what they were really saying is that they want to transform the classical definitions of a client-server architecture, because now every host, every machine that runs your applications can have its own dedicated data server. This becomes really powerful because now you don't have any contention for resources at the network. All your hosts just have a global view to all of your SSDs, which of course can support a really high level of concurrency. And so the net effect of it is, forever you would have, like, let's say, just an anecdote, you have 1,000 nodes in your cluster and you'd have 100 file servers. Now you have 1,000 nodes in your cluster and you may have 2,000 file servers because each machine has 2 network adapters that both have file servers on them. So completely changing notions of contention, power management, and things like this, and it's all done with this platform. A platform that, as I mentioned earlier, it goes well beyond the classical definitions of a storage system, and I'll explain why that is in a moment. But we wanted to start by building the right data foundation for unstructured data. And my background is in parallel file systems. I was previously at DDN. Prior to that, I was in the original Lustre team. And we made the very conscious decision not to build a parallel file system with a classic parallel file system driver that you have to run in your host. The reason for that is that's a level of complication that you don't need if you can twist NFS, which is a standard access protocol, to get the performance that you need. Our architecture is entirely parallel. You don't need PNFS or anything like that. We've solved these problems at the server level such that the host can be really clean. NFS with support for RDMA and multipathing, even GPU direct storage. When NVIDIA took the covers off of GPU direct storage, they used VAST as the example of performance in this space, not only because NFS was simpler for the enterprise customers that they want to get to, but it was also the fastest implementation of GPU direct storage that they found. And so everything is multi-protocol, everything is built in-house, everything is engineered by, we have roughly 500 engineers in the company today, so we're really working hard to build an enterprise appliance experience, and at the same time we want the most standards presentation that we can give so that customers can immediately take advantage of the platform. Last year we announced something called the VAST database, which you can think of as a transactional data warehouse. This becomes really important when you start to get into AI environments that turn unstructured data into something that can be structured. Well, that structure needs to live somewhere, and our customers are ingesting data to the tune of hundreds of thousands of files per second. And so we decided to reinvent the data warehouse. And here, imagine a system that's SQL addressable, Kafka addressable. You just stream data into the system at whatever level of performance that you want. It supports millions of inserts per second. And when you go query that data, we turn rows that you write into columns. Columns that can be analyzed faster than any other data warehouse in the world, because we've taken advantage of Flash, and most of the data science industry hasn't really been able to keep track of that, largely because they're dependent upon different cloud services. And so when you put it together, now I have a system that has the ingestion properties of something like the fastest streaming system in the world, the query properties of the fastest data warehouse, and the scale and the cost of a data lake. The final aspect of the system comes in this year when we add the runtime natively into the system. Event triggers that our customers can program that call functions that can start doing things like inferring on data and what have you. And really what we're trying to build is a data flow computer in software. And why do we do it? Well, if you think about the totality of an AI pipeline, it is far more than just, I need a file system for training. Customers have to ingest data using standard protocols like NFS or S3 or Kafka even. Then they have to prepare data. Typically that happens with Spark. Spark demands and respects things like data frames, and data frames help data scientists do things like interrogate on data using SQL. And so now you need a different set of tools historically to go and just manipulate data so that you can train on it. Training needs POSIX, it needs RDMA. That's starting to change to S3, and of course you can do both with us. And then finally, once I have my model quantized, I have to deploy it on infrastructure that's required for things like AI inference. And if you're at all regulated, or if you're just making sure that your model doesn't drift at all, then you want to capture all the queries or the prompts, you want to capture the responses, and you want to bring that into the system using data warehousing tools that of course we have native to the platform. And so you put it together, this is the only full stack solution for pretty much everything in the market. And why customers like us, I'll build this out because I screwed up the animation. All the enterprise features are built in. The conventional wisdom in the last 20 years is that parallel file systems make you sacrifice data management and simplicity for performance. But now you can get both, and I'll tell a few case studies on this. Number two is, our approach to storage efficiency enables full tier consolidation, because now all of your active data can live on NVMe affordable flash. And I think the thing that, as I talk to customers more and more, what they most value is uptime. I was in Germany yesterday, a customer told me they're taking a full week outage to upgrade their Lustre system, and I couldn't think of something stupider to happen in the world. Like, machine costs $30 million, I'm going to take it down a week every year just so I can upgrade my file systems. People are taking crazy pills. So we built a system that should be used by banks, should be used by large-scale government organizations, and we care deeply about uptime. On average, in our field of systems across 20 exabytes, we're operating at 5 to 6 nines. Everything is always online from a maintenance perspective. And what we do is we keep clusters running better than anybody else. Now, where does that happen? One of the case studies that we love to talk about is TAC. TAC engaged us last year with an idea that they were going to start moving away from Lustre. It was the biggest source of complexity in their environments. And so they started evaluating new file systems, including some of the most high-performance ones in the market. They thought VAST was going to be the slowest. First of all, when they realized that at 2-to-1 data reduction, they could consolidate their environment such that their flash and their hard drive environment could be all flash, they realized they could afford more flash than they otherwise thought they could. Number two is our workloads scale 10 times better than Lustre. And at equivalent scaling points, we could show 30% better performance. So like, holy crap, with NFS we can get to a better performance than we thought we could only do with a parallel file system. Number three is, as they went through standard administration tasks and the system had issues, it never stopped. Like they had a number of hardware failures that triggered an upgrader that was failed, and it didn't matter. The system was always online, even running multiple versions of code, and this to them was a big breath of fresh air. Now in Italy, we've had a similar experience with Cineca. Cineca is in the process of redefining massive scale computing. Earlier this year, they selected VAST for the basis of their cloud. It's a full stack system for their HPC, for their AI, even for their analytics pipelines. And they are a very, very vocal supporter of VAST. If you have the chance, please talk to them. Now, the last thing I'll leave you on is a lot of what I just talked about is mostly training or HPC. We do see a wave that's about to hit us very, very strongly around generative AI as it relates to deploying this into standard environments. And what's very clear to us is that AI models have limits. One is you can't train enterprise security into a model. It doesn't know how to enforce things like ACLs. So AI without enforcement is kind of just, it's not practical for secure enterprises. Number two is data changes all the time, whereas people only periodically fine-tune or update their models. And so if your business is living in business time, then periodic training just doesn't work for that application. And that's why data is now starting to get vectorized. So if you think about this, you have now models that can go out and ask questions to data stores that have been contextualized by something called vector databases and embedding models. Embeddings are basically numerical signatures of data that basically provides context back to an LLM in the form of an answer that gets created from facts that are within your unstructured data. And so you can organize this data into like similar group clusterings using similarity clustering, which is the same type of algorithm that we use for data reduction. And as I talked earlier on main stage, what I see happening over the next couple of years is you're basically going to have the death of file systems as these data platforms figure out how to go and structure all of your data, not just the data that is classically fit into a data warehouse, because everything that doesn't fit into a data warehouse, I can still warehouse the signatures of that data and provide that to LLMs to make that data conversational. So I think it's going to be the end of file systems. NVIDIA describes a pipeline as such. You basically take a bunch of documents, you chunk them up, you apply some metadata on top of it, and what comes out of that through some inference microservice is something called an embedding. That embedding sits in a vector database, and now as you start to introduce agents into your environment, once a prompt gets issued to an agent that the agent doesn't have enough confidence in, before it starts to hallucinate, it can go out to either a vector database to get an answer from its unstructured data, or it can go out to a classic data warehouse and get answers from structured data. Now, the thinking is, if I make my vector search process really fast, that's the definition of real time. As we looked at the market opportunity, what we realized is that Google-style architecture has been plaguing vector databases, it's been plaguing data warehouses, it's even been plaguing file systems where, today RAG systems will periodically get indexed, whereas your enterprise file systems are seeing churn all the time. That same dynamic is also true of data warehouses, where you might have some event bus over here, and the data warehouse over here, and the event streams are only coming into the data warehouse periodically. So there is no definition of real time in the market as it relates to AI retrieval until now. And so, so we're working to build something that is much better. Candidly, we're calling it the Insight Engine. And imagine a system that works like this. Query comes in, agent gets a question that it can't answer, it will respond to that because it has a high enough confidence score in its answer. When it doesn't know, it goes out to query a SQL addressable vector database that we can update in real time with the VAST database. Now that has already worked in conjunction with what we call the VAST data store, which is where all your unstructured data is. And every new file, every new object that comes into the system is instantaneously indexed or vectorized and then added to the index. Similarly, when your data gets deleted, that's removed from the index, and all ACLs are presented right through the index. So you have this thing that's secure in real time and massively scalable that can just talk to AI agents in the way that AI agents want answers. Now, on that tone, the VAST database also provides the opportunity to consolidate your event bus and warehouse into just a transactional data warehouse. What the agent gets is always a real-time look at all of its data all the time. And we think we're pioneering a lot of new ground here. The first real-time retrieval system with a vector database that can support trillions of vectors. Why is this important? Well, as these technologies start to get applied broadly within organizations, you won't have like data curators that just need to go and scan a few documents and say, here's the facts I want to add to my vector database. That's not how it's going to work. NVIDIA and the community are working so quickly to improve the state of inference models that at some point people are just going to let them loose on all of their enterprise data, saying, go classify, go index everything, and that will create a scale problem, both in terms of an organization being able to view all their vectors, and second, in order to be able to search through that vector space in constant time. And so we've solved that problem. And then more importantly, we're doing it where it makes sense, right? A lot of these retrieval pipelines will say, just copy your data to the cloud from your file servers, and then we'll go and run it, some process on it on an object storage system. That to us is totally ridiculous. File systems need to be self-describing, and vectorization and AI embeddings is the way to do it, and VAST is going to bring it to the masses. So our real secret is that we built this kind of real-time web-scale data flow computer that's designed for AI inference and data classification, but it's also a kick-ass file system, also a very, very good object storage system, and we would love the chance to work with you all on this. So, if you want to learn more, on October 1st, we're hosting a big introduction of this product. This came out on the web yesterday. These are all the organizations that are talking about working with VAST. And this is my goofy-looking CEO, and that's NVIDIA's goofy-looking CEO, and we would love for you to join. So thank you.